Okay, so you recognize this room? It's kind of weird. There's nobody in the room except for me. And there's a question about whether we'll be able to keep this room. But anyway, I'm going to give this a try, see how this works. And if, in case you're curious, today is Wednesday, March 18th. So it's the first week in the semester that doesn't exist given the new rules. And I'm using the in-room Panopto recording system, which we've noticed before, the camera in the back and the monitor. And up here, this white thing hanging from the ceiling is a mic, a wired mic, so I don't have to use a wireless mic. And I hope that my voice comes through clearly. I was in here with the IT guy yesterday, checking it out. It seemed to work out pretty well. But anyway, I know this is going to be kind of weird lecturing to empty room, and you people are where you are. I don't know when you're watching this, or how you're watching it, or what time zone you're in, or whatever. And I kind of have to pretend that you're here, because part of giving a lecture is connecting with the people in the room. And so I don't know how I'm going to do that. I'm going to try my best, and maybe even call on some of you to answer questions. But as always, first off, are there any questions? Victor. Okay, so why aren't we having the midterm today? We're not having the midterm today because you're not here. Okay, that's why we're not having the midterm today. We'll have to figure out how to do that. I don't know how we're going to do the midterm. I haven't figured out the midterm and the final, but whatever. We're going to get back to that later on. All right, so let's move on and talk about stuff that is hopefully of interest to everyone. Remember what we were talking about last time. We finished up, and by the way, the resolution on this camera is pretty good, so if you can't read the writing on the board just by looking at the picture that you see now, you can always blow it up on your computer, and I don't think it's going to fuzz out on you. Like, I can practically read this sign from here, so it's pretty amazing. Anyway, so we finished up this sort of metropolis / simulated annealing stuff, and we talked about some of the history and notably the whole idea of computers coming along and the idea of randomness and computers being useful sort of taken in tandem and that leading to Metropolis Hastings, and then people thinking about evolutionary stuff starting with Lawrence Vogel, and then John Holland came up with the thing we started talking about at the end of class last time, just scratch the surface. So we started talking, not talked, about genetic algorithms. And so that's where I want to pick it up today. All right, so what are these genetic algorithms? What's going on with these things? You start with, so this is what they're for. They're for solving problems. Okay, so you start with a problem and an associated set of candidate problem solutions. So a set cap phi of candidate solutions to some problem. So the reason I'm calling this phi, same reason we use the letter capital Phi when we're talking about biological evolution. The idea here is phenotypes. Okay, so how well you solve the problem, that's your phenotype. And the way you summarize how well a given solution solves a problem is by this fitness function. So a function f that maps every phenotype to a real number. So it's a function f for phi to the reals. And this is a fitness function of sorts. And one of our background assumptions throughout this discussion, and it's necessary, this is a necessary assumption in some contexts and not in others, is that this is always positive. In other words, f of phi is positive for all phis in cap phi. And the idea here is that f of phi larger that's going to correspond to phi being a better problem solution. So a better solution to the original problem. Okay, so you have that. And then you have a space, capital G, of genotypes. So this is the set of all genotypes okay. So for a standard genetic algorithm, this is going to be the set of all bit strings of some fixed length, say capital L. So for the standard genetic algorithm, and this is an abbreviation I introduced you to you last time that I'm going to follow through with for the rest of the discussion. So for the standard genetic algorithm, G is going to be the set of all bit strings of some fixed length L. Capital L. And we have defined on this set of genotypes a function G that maps genotypes to phenotypes. It maps bit strings to problem solutions. And this is the encoding. So it's a way of representing, you represent every possible problem solution phi as some bit string or set of bit strings, and the comment here is that G is surjective in the sense that every phi in phi has some bit string encoding in G, but it's not necessarily injective. In other words, different bit strings of length L can encode the same problem solution in cap phi. So it's possible for a given phi in cap phi to have multiple encodings. Okay, so those are some basic building blocks. And by abusive notation, as we'll see later on, we're going to talk about f of a bit string rather than f of g of a bit string, but we'll get to that as we go along. So anyway, given these building blocks, problem solutions, fitness function defined the problem solution set of genotypes, how does a genetic algorithm work? So for a standard genetic algorithm, so the SGA evolves populations of genotypes of bit strings. And generally what's going to happen is that you have some fixed population size, little n. So let n equal the population size. And this is fixed throughout. And generally, we're going to assume that n is an even number for reasons that will become clear as we discuss this. So generally, n is even. You'll see why. Okay. At any given time t, t is going to be an integer time. And I hope this mic picks up my voice when I'm facing like this way, looking at the board. Who knows what's going on with that? So at any given time t, I'm going to let p of t be the population at time t. What is p of t? As usual, p of t is going to be a multiset of bit strings. So for each t, p of t is a multiset of bit strings of length L and size n. So p of t contains n individuals. for all t. And here, an individual, that looks a little u-ish, so let's make it more n-ish. An individual is one string. Okay, so two different copies of the same string represent two different individuals in the same population. Now, the standard genetic algorithm involves populations of bit strings, these p of t's. So the algorithm is going to takes p of t, so it takes p of t and generates p of t plus 1, etc. as you go along. So in some sense, what the algorithm is doing is hopping around in the space of all populations. So thus, it quote-unquote searches or quote-unquote hops around in the set of all populations, set of all possible populations. Now you have counted on one of the homework problems how many populations there are in this context. So we saw on the homework that there are this many. Two to the cap L plus n minus 1, choose n, or 2 to the L plus n minus 1, choose 2 to the L minus 1. There's the same numbers, okay? Different populations. This is a huge set. So there's no way that in a given run of a genetic algorithm, you're going to come even close to exploring a tiny fraction of that set. Okay, so you never, when running an algorithm, see a tiny fraction of that set for reasonable values of cap L and rho n. Okay, so anyway, how does the genetic algorithm go from population of time t to population of time t plus 1? It depends, okay? It depends on how you select parents for the next generation, whether you keep some of the current generation that are particularly good in terms of high fitness, whatever. There's all kinds of ways that this can happen, okay? So generally, the evolution from p of t to p of t plus 1 is going to depend on some user choices. And specifically, it's going to depend on things like that we call things like genetic operators, selection methods, stuff like that. So various genetic operators, selection methods, etc. Okay. So we're going to talk about a few of these different genetic operators selection methods. Generally what happens is that, so usually what you're going to do is, so you're going to select from p of t plus 1, or sorry, from p of t, parents for the strings, the individuals in p of t plus 1. All right, so how do we do this? That depends, okay? How many do we pick? What we're going to do, and this is why we assume that n is even, okay, we've assumed that n is even. So what we're going to do is we're going to pick somehow, or later, n individuals from p of t to serve as parents for p of t plus 1. You pair them up into pairs. So how many pairs do you have? You have n over 2 pairs. So pair them into n over 2 pairs. Okay? So now you have pairs of parents. Each pair of parents will generate 2 offspring. Those offspring will be members of P of t plus 1. So each such pair gives rise to 2 offspring. That's one word. And those guys are going to be members of P of t plus 1. So, you have n over 2 pairs. Each of them gives rise to 2 offspring. Therefore, you have n members of P of t plus 1. 2 members of P of t plus 1 come from each pair of parents. Okay? All right, so how does this giving rise to happen? How does a pair of parents give rise to a pair of offspring? So, how does a pair of parents give rise to a pair of offspring? Okay, so how does this work? Here's where the genetic operators come in. Okay, Priyanka? Okay, yes, every pair of parents gives rise to exactly 2 offspring, period. That's the way this works. Okay? I hope this pretending to have people in the room and asking questions doesn't get tiresome. Okay, I thought you were going to say something, Scott. Sorry. All right, so anyway. You have these 2 strings. You have a pair of strings, and given a pair of parents, first, you cross them over. With some probability PC. This is what people call the crossover probability. And you've all read about this. You read about this when you read the first chapter of Mitchell's book, and you did problems at the end of that chapter for homework 1. And in general, in real life, the original standard genetic algorithm that Holland came up with, the probability of crossover was relatively high. In other words, generally you're going to be crossing over 2 strings with probability around 75%. So usually, at least in the olden days of GAs, PC was on the order of like 0.75. Okay? So that's crossover probability. What does crossover mean? There's various kinds of crossover. So what you want to envision is the following. You have a pair of parents and you flip a coin that has probability PC of coming up heads. You flip that coin. If it comes up heads, you cross them over. Looks like we have a visitor. This is Patty Gagne. She's the building manager for...
Look, he's going to be safe.
Now, she brought me some Lysol wipes here. Ooh, so I can sneak into this room anytime, eh?
Yeah.
Excellent. So, see? Connections by you.
Take care.
Yeah. This is EC 4271, by the way. And I even have some wipes to wipe down the buttons on the computer when I leave, so I don't leave my germy. So that's taking the role of the 3-minute break, right? Okay. Actually, I'm going to put this key on my key ring because it's like an important key, and I don't want to lose it. I hope you guys are having fun with this. I miss you so much. I mean, it's terrible, you know. You try it. I mean, look, I've been at this for 38 years, and until today, I have never given a lecture to an empty room. I've never even practiced talk in front of an empty room. The closest thing I can remember to this in recent memory, what's not so recent, was when I was in 7th grade, back in 1966-67, I played Scrooge in A Christmas Carol. We put on a production of that for Drama Club. And I remember pacing up and down my living room at home, going through the lines, any fool who walks around with Merry Christmas on his lips should be boiled in his own pudding and buried with a stake of holly through his heart, that kind of thing. You can imagine me as Scrooge, eh? All right. Sorry. Just reminiscing there. Okay, so crossover probability. Crossover happens with probability, say, 3/4. What exactly happens when you cross over two strings? There's different kinds of crossover. Okay, so different kinds of crossover. And probably the most common one that you see is what they call one-point crossover. So what happens is, say you pick a crossover point uniformly at random from the L-1 possibilities. Okay, and I'll do an example on the next board in a second so you see what I mean by the L-1 possibilities, and then you cross them over, cross the strings over. At that point. So for example, suppose, say, L equals 8. So e.g. L equals 8. And you have two strings. The parents are, say, 0, 1, 0, 0, 0, 1, 1, 0. Is that 8? Yes. Excellent. And the other parent is 1, 0, 1, 1, 0, 0, 0, 1, say. Okay. Now, L is 8. What do I mean by the L-1 possible crossover points? I mean the interstices, so to speak, between the bits. So there's 8 bits in a string. There's 7 interstices, 7 places where you can pick to cross them over. So you flip a coin, and suppose you pick this as your crossover point. So you flip the coin, the uniform coin, or a 7-sided die, or whatever, like Dungeons and Dragons might have something like that, and to choose the crossover point. And say we picked that one there. Then the offspring are 0, 1, 0, 1, 0, 0, 0, 1. So you take the left half of this parent and the right half of this parent, and then down here you have 1, 0, 1, 0, 0, 1, 1, 0. Left half of this parent, right half of that parent. And I'm not making any judgments about, there's no mother, there's no father, there's just two parents. They could be anything. Okay. That's 1-point crossover. Then there's 2-point crossover, 3-point crossover. How do you do those? Well, you pick 2 points. You pick a pair of crossover points uniformly at random. And there's like L-1 choose 2 ways you can choose a pair of interstitial points. And you take first third of one parent, middle third of last parent, last third. When I say third, I'm using that word in a general sense, just meaning to the left of the first interstitial point, between the two, and to the right of the right one, etc. There's 2-point crossover done in the obvious way. So you have a pair of these, what you might call breakpoints. And there's also uniform crossover, and this is kind of a weird one. And in some sense, though, you think, oh, well, maybe, this makes a lot of sense for shuffling purposes. Uniform crossover is the following. Okay, for each position in the string, you do this twice. You do this one for each of the offspring. You flip a coin and decide which parent gives the bit for that position. So for each offspring, what you do is you flip a fair heads and tails coin. So you flip the coin for each bit, position to decide which parent it comes from. So if I call this parent the top parent, this parent the bottom parent, I flip a coin and it comes up heads, I take the top parent's first bit for the first bit of the offspring. Flip it again, it comes up heads, I do that again, I take 1. Flip it again, it comes up tails 4 times in a row, then I have 1, 1, 1, 1, 1, 0, 0 for the next 4 bits, and so on. I have to do that all down for the first offspring and then do it all for the second offspring. That's uniform crossover. Okay, so that's the first thing you do. You have your pair of parents, you cross them over, maybe. Cross them over if the PC coin comes up heads. Then what do you do? Now you have these offspring, and what do you do to the offspring? You mutate them bit by bit. So having completed crossover, step, you go through the two crossover products, the two offspring, bit by bit, and mutate each bit with probability p sub n. So flipping each bit, so 0 becomes a 1 and 1 becomes a 0 with probability p sub n, the mutation probability. And usually it's rather small, at least in the traditional GAs that Holland put together. So p sub n is on the order of, say, 1%, like 0.01, say. It's a small probability. And having completed that mutation step, that gives you your offspring. Or at least your members of P of t plus 1 that come from these two parents. So having completed the mutation step, you throw the resulting pair of strings into 2p of t plus 1. Okay. So that's how p of t leads to p of t plus 1 once you've selected the parents. You need to do that. Okay. And the user choices here, by the way, in this part of it are PC, the type of crossover, and PM. So the user choices we've considered so far. So in this part of the picture are PC, PM, and the kind of crossover you use. Be it 1 point, 2 point, uniform, whatever. Okay. So, what about the selection issue? So how about selection? How do the parents get selected? And by the way, when I'm done talking about how these GAs work, I want to contrast them with our earlier in the semester discussion of biological evolution, just to see where the complexity gets completely stripped away and how one might perhaps take inspiration from biological evolution to do something more sophisticated. But anyway, how do the parents get selected? Well, there's lots of different possibilities. Here, each of these possibilities is a value of a user choice. Okay. So one we're going to talk about at length is fitness proportional selection, and there's some debate about whether it's fitness proportional or, okay, I could see Priyanka smiling right now because I'm worrying about a word again, but fitness proportional, which is what I use, or fitness proportionate. And if you look in the book, you'll discover that Mitchell uses both. So I don't know whether that means she forgot to change them all to one when she settled on one, or whether she thinks they're both okay and she wants to communicate that subtly without saying it out loud. I don't know. I say fitness proportional. You could say fitness proportionate if you want. And we're going to talk more about that later. Okay. Another kind of selection, and generally, by the way, we're going to learn that this fitness proportional selection usually doesn't help, solve problems. And you need to include some kind of elitist selection. So various kinds of elitist selection. So some examples. What do I mean by this? What does elitist selection do? It tries to preserve progress you have made already. Okay? So, turns out fitness proportional selection, you can throw away all the progress you've made if you make an unfortunate pick of the parents. But with elitism, you're not going to do that. So here's some examples of kinds of elitism. Keep the top, quote unquote, say top 10% of P of T as members of P of T plus 1, P plus 1, and you use some random selection method like fitness proportional. So use, for example, fitness proportional selection to pick parents for the remainder of P of T plus 1. So to put some numbers to this, if, say, n, remember what n is? N is the population size. It stays the same throughout. If n is 60, so revolving populations, each of which contain 60 bit strings. You might form P of T plus 1 from P of T by, first off, demanding that the top 6, so immediately put the top 6 fitness-wise from P of T into P of T plus 1. And then, and this you might decide not to use fitness proportional selection, but that's a possibility. You pick 54 parents from P of T for the other 54 members, individuals, whatever you want to call them, of P of T plus 1, and apply the genetic operators, etc. Okay, now someone at this point always asks the following question. Jonathan. Yes, that's exactly the question. Did everyone understand his question? Okay. His question was the following. Having put the top 6 guys from P of T into P of T plus 1, do I include them in the part of P of T from which I select the 54 parents for the other 54 members of P of T plus 1 or not? Since they're already taken care of, do I even include them? Like, you can or you can't. You can decide that. And as it happens, I would be inclined to include them because say you have one of the top 6. That's going to make a really good parent, even if it doesn't pair with someone who's high fitness, something like that. Okay, so that's a good question. Keep the top 6, throw them back into PFT, and from PFT pick 54 parents for the next generation. For the remaining entries, the remaining individuals in the next generation. Okay, so that's one thing you could do. That's one kind of elitism. Another kind of elitism is like, and this is kind of the negative elitism. So, negative version of this. You throw out the bottom 10% of PFT. Okay? You don't even consider them when you're picking parents for PFT plus 1. So, throw out the bottom 10% of PFT. And use only the top 90% to generate parents. For PFT plus 1. Okay. So that's a negative side of elitism. And another kind of elitist selection is, this is not quite, well, since it's not really quite elitism, I'm going to talk about it as a separate tournament selection. This is tournament selection of various kinds. And again, you know, there's no one kind of elitist selection, there's no one kind of tournament selection. Okay. So how does tournament selection work? You pick your parents for P of T plus 1 as follows. By doing what I'm about to describe, doing this, how many times? N times. Each time you do this, you're going to create one parent. All right, from P of T, pick, without replacement, Q, individuals. And you can do this any way you want. You can do it uniformly at random, say, over P of T. So the first one you pick, you're picking from N, so it's a probability of 1 over N that each guy gets picked. Then there's probability of 1 over N minus 1 that the next guy gets picked, whatever, but it depends on who got picked the first time and so on. Anyway, you pick Q individuals without replacement. That's to say, I pick the first one, don't put it back. Pick the second one, don't put it back, and so on. Now you have Q individuals, and you run a tournament between these Q individuals. You say, okay, which one of you Q has the highest fitness? I will keep you as a parent for P of T plus 1. So take the highest fitness string individual in this list from these Q, and put it in the pile of parents for P of T plus 1. And in this way, you generate n parents, because you do this n times. So you, from these Q, and use it as a parent for P of T plus 1. Okay, so you generate n parents that way. Now, a useful thing to do is think about the limiting cases here. Okay, limiting cases. Where, applied mathematicians like to think about limiting cases. Like, for example, not to be topical, but say you're in the middle of an epidemic, right? Or you have some disease. Now, here's extreme cases. One extreme case is no one ever gets the disease, okay? And say the disease runs its course in 14 days, right? The other limiting case is everyone gets the disease on day 1, right? Which means everyone's over the disease on day 14, so game over, no more epidemic. But what happens? Well, because so many people are sick, lots of people die. So that's the tall curve. And if you flatten the curve, you lengthen the length of the epidemic, but you reduce the number of people who die. Okay, so those are those trade-offs we're talking about. It's all over Facebook. I mean, you're probably sick and tired of thinking about this stuff. It's depressing. The whole thing, what we're going through now is really depressing. All right, but we're going to try to be positive here. Okay, so anyway, you got this, you got the tournament selection, use these guys as parents for PFT plus 1. Okay, so that's another way. What are the limiting cases? Okay, so limiting cases. How about Q equals N? Anybody? Q equals N. Remember, N is the population size. Okay. So suppose I pick N individuals without replacement. Remember, that's part of the deal. Uniformly at random from P of T. What N individuals do I pick? Scott. Yes. You pick all the guys in P of T. Okay. Does everyone get that? I see in my imagination, some confused faces. I'm running a tournament between Q individuals to generate each parent. How do I pick those Q individuals? I pick them without replacement from P of T, one at a time, uniformly at random. So I pick the first guy from P of T, put it over here. Now I've got N minus 1 individuals left, and I pick uniformly at random from them, and I do that N times. I'm going to exhaust P of T. All right? So the N guys I choose for the tournament are all of P of T. So Q equals N. Thus, each tournament pits everybody against everybody, so involves everyone. And once in a while, I'm going to lapse into anthropomorphic talk, talk about individuals and populations as if they were animate beings in P of T. Okay, and so what's left over after each tournament? The highest fitness individual, or one highest fit, there could be tied for the highest fitness, but highest fitness individuals in P of T. So the only parents you generate are individuals of max fitness. And so if you had, say, only one string whose fitness was the max of all fitnesses of all strings, then all of a sudden you would only have one string as the parents for the next generation. And of course, that wouldn't necessarily kill you because, if you go through the mutation process, you're going to mutate away from that perhaps, but whatever. That's one limiting case. The other limiting case is Q equals 1. And that's just picking uniformly at random parents. So this is the same as picking N parents for P of T plus 1 uniformly at random with replacement from P of T. Okay? And when people talk about these things, sometimes they talk about, okay, what if I change this user choice? Am I introducing higher selection pressure or am I lowering the selection pressure? In these cases, the Q equals N corresponds to high selection pressure What do I mean by high selection pressure? I mean that your relative fitness has a lot to do with whether you survive, quote unquote. Okay? Whereas Q equals 1, low selection pressure. You look at Q equals 1, you're picking your parents uniformly at random from P of T with replacement, and what that means is fitness plays no role in whether you get selected. So fitness plays big role in whether you're selected. And in this case, fitness has no role, 0, in whether you're selected. All right. So there. So that's tournament selection. And there's lots of other kinds of selection. There's one, we've talked about Boltzmann. There's one that people like to call Boltzmann selection. So this would be what, number 4? Is that number 4? Yeah. Boltzmann selection. And that would be that you say you pick a given individual according to a Boltzmann-like distribution, whatever that means on P of T. So given X and P of T, you draw parents the probability of selecting X on any one parental draw. And this terminology, parental draw, is going to make a little more sense in a minute when we talk about fitness proportional selection. Okay? But the probability of selecting X on any one parental draw is going to be this. It's going to be e to the beta times the fitness function of X, fitness of X divided by the sum over all strings in P of T, e to the beta times the fitness of those strings. Okay, now obviously that's Boltzmann-ish because it has exponential, and I put a beta in there to make you think Boltzmann, right? And whatever. And whether beta, the higher beta is, the more selection pressure, the lower beta is, the less selection pressure. You're gonna actually look at this on homework a little bit at some point. But anyway, so you'll understand this better when we talk about fitness proportional selection, and etc. So there's lots of other kinds of selection that you can do. All right, so now what we're going to do is we're going to talk in a little more depth about fitness proportional selection, and we're going to talk in particular about what I would call debunking the whole schema theory idea, you know. But before I do that, what I want to do is I want to just look broadly speaking at what we're talking about here and see how, as I mentioned earlier, I want to do this, how the complexity of biological evolution is totally out of the picture here, that you have completely modeled that away, or at least for practical purposes you're not addressing it. So what does this kind of algorithm strip away from biological evolution? Okay, so here's a little aside. So how does this SGA simplify, quote unquote, and that's putting it mildly, okay? Simplify what goes on in biological evolution. Okay, and here's where, like, ordinarily, now is when I take the 3-minute break, and you know, you may wonder, like, 3-minute break, you know, we're doing that the whole semester, and I always do that in my 75-minute classes. Why do we do it? Well, it's as much for me as it is for you, okay? However, since I don't really know this video equipment yet completely, and I'm scared to pause it, right, for fear of, like, losing the recording, heaven forbid, I'm just gonna like stand here for a second, and one of these days I'll come in and I'll like do a beta test and figure out whether I can stop it and start it up again. But for now, I'm just gonna stand here and pause, because the break is just as much for me as for you, and I'm just not gonna say anything for a second, because it's relaxing not to say anything for a second. So. Okay, so anyway, how does the SGA simplify what goes on the biological evolution? Remember the picture we had of that? So we had a picture like this. Okay, you had, what did we have? We had a G, so that's a set of genotypes. And then we had this development process that takes the G's into V's, right, phenotypes. And every guy in this here is a pair, a G comma phi, or something like, yeah, some genotypes to phenotypes. And then phenotypes get selected according to a selection operator, right? And that leads to the guys who are going to reproduce, right? And they undergo these genetic operations to give rise to the genotypes of population of time t. So let's say GT gives rise to phi t, gives rise to RT, gives rise to GT plus 1, and then it goes like that again. Okay? Remember that? I hope. All right. And I said, all right, the squiggly arrows with the delta, the sigma, the gamma, they all correspond to lots of random effects coming in, lots of random effects. So the genotype to phenotype development, lots of random effects. The selection, lots of random effects. And the random effects here, the gamma, involve things like, crossover and mutation. Now, the GA strips away, in some sense, the least from this part of the picture. In other words, the GA randomness around, so the SGA, I'll say SGA, try to keep uniform notation here, around, so involving, say, crossover and mutation. That, in some sense, that's a reasonable kind of model for the gamma process. So models sort of a legit gamma type process. Okay. But the other two, delta and sigma, on the other hand, are things that the GA basically, ignores, essentially. Or at least, in the case of sigma, ignores the really important fact that it's endogenous rather than exogenous. So let's look at the delta and sigma things and see how the GA disposes of them. So unlike the gamma, the delta and the sigma, the SGA sort of disposes of much complexity of the delta and sigma processes as follows. As far as delta goes, essentially the GA ignores that. There's this mapping, a deterministic mapping from genotypes to phenotypes. So this is ignored completely. So we have this deterministic mapping. And like I said earlier, it could be many to one, but at least it's deterministic from genotypes to phenotypes. No randomness at all. Okay? So all the complexity and wonder of development and biological evolution, gone completely. What about sigma? Sigma. Selection is based on, in any of these selection methods we talked about, fitness proportional, elitist, tournament, whatever. Any of these selection methods, SGA version is based on an exogenous fitness function. Now again, exogenous fitness is coming from the outside. In particular, how fit an individual X in P of T is depends only on X and not on who else is in P of T. And we know that's not the way it works in biological evolution. Fitness, who survives to reproduce, that's endogenously determined. No one assigns a fitness to everybody. Okay, so that's not at all like the endogenous fitness in biological evolution. Okay, so that's just a little aside. I wanted to point out like how stripped down the genetic algorithm version of evolution is compared to biological evolution. If you didn't see that already, now you see it. All right, so now let's get back to talking about fitness proportional selection, because that's what most of Mitchell's chapter dealt with. And also, it's the kind of selection that Holland proved the schema theorem about. But anyway, we'll see how this works. So what about fitness proportional selection? And I'm having trouble with the sleep, so pardon me, whether you like it or not. Okay, so now a closer look at fitness proportional selection. And here, I want to emphasize that we are abusing notation a little bit by putting strings inside of F's, because F's really operate on phenotypes. Okay, so here's the slight abuse of notation, which we've already used. So where did we use it already? We used it when we talked about Boltzmann selection. And it goes like this. If X is a string, what we use this notation, F of X, fitness of X, instead of F of G of X. Remember, fitness applies to phenotypes officially, okay? So phenotypes are not X's, they are G of X's. Their problem solution represented by X has a certain fitness. We call that F of G of X. But I'm going to use this notation to represent this thing. Just save space. And if you don't like it, that's fine. But that's what I'm going to do. Okay. So what does fitness proportional selection mean? So fitness proportional selection works like this. What we want to do is, for each X, in P of t. What we're going to do, by the way, we're going to generate the parents for P of t plus 1 by picking n individuals from P of t and pairing